Welcome to this session. This session, we are going to introduce a concept of properties of determinants that can help us to evaluate determinants of matrices. So property number one, states that if you interchange any two rows or any two columns of a matrix or of a determinant, then the value of the determinant doesn't change. So the value of the determinant remains unaltered has to mean remain the same if rows are interchanged into columns or columns into rows. So that's a powerful tool, that interchanging any rows and columns doesn't change the value of the determinant. So e.g., determinant of the matrix A1, B1, C1, A2, B2, C2, A3, B3, C3, the value of this determinant is the same as determinant of A1, A2, A3, B1, B2, B3, C1, C2, and C3. If you observe keenly that A1, B1, C1 is the first row, now become the first column. A2, B2, C2 is the second row, this now becomes the second column. A3, B3, C3 is the third row, but here now is our third column. So it's just to say that the determinant of a matrix A is the same as the determinant of the transpose of the matrix A. So that's the first property. Property 2, if two rows or two columns of a determinant are interchanged, then the sign of the value of the determinant changes. That if you switch two rows or two columns of any determinant, then the sign of the original matrix or the sign of the original determinant changes. If it was negative, becomes plus, and vice versa. E.g., the determinant of this matrix A2, B2, C2, A1, B1, C1, A3, B3, and C3 is the same as negative of the determinant of A1, B1, C1, A2, B2, C2, and then A3, B3, and then C3. What's happening is that now in this original determinant, the first row is now the second row in this new determinant, and the second row now takes the first row position, third row is fixed. So here what happens is that row 1 has been interchanged with row 2. So whenever you interchange any two rows or columns, then the sign of the determinant changes. Property number 3. That if two rows or columns of a determinant are identical, then the value of the determinant is 0. So e.g., the determinant of this matrix A1, B1, C1, A1, B1, C1, A3, B3, C3 is 0. Since row 1 is the same as row 2. So whenever any two rows or any two columns of a matrix of a determinant are the same, then the value of that determinant is 0. Or simply, whenever two rows or two columns of a square matrix are identical or are the same, the value of the determinant of that matrix is just 0. Property 4. If the elements of any row or column of a determinant are multiplied by the same number, or say scalar, then the determinant is multiplied by the same number or scalar. That whenever we have a determinant being multiplied by a common scalar or a common number, and in any row or any column, there's a common scalar multiplying all those elements, then the value of that determinant is simply the value of that scalar times the determinant of the matrix before you multiply that scalar by the row or the column. So e.g., if we have a matrix, remember a matrix, this is the sign we show by a matrix. So let this denote the matrix, the determinant A1, B1, C1, A2, B2, C2, and then A3, B3, C3, and this be the determinant of K A1, K B1, K C1, and then A2, B2, C2, A3, B3, C3. So let's have these two determinants. The first determinant is A1, B1, C1, A2, B2, C2, A3, B3, C3. And then we have another determinant where the first row is multiplied, elements are multiplied by a constant K. Then this determinant is the same as taking that constant, multiplying by this determinant A1, B1, C1, A2, B2, C2, A3, A3, B3, C3. Already the same as K times that determinant delta. Or similarly, if we have, so if I have, say, determinant 3, 6, 9, 2, 5, 7, 1, 0, 8 is the same as, because the first row is you can factor out 3. So the same thing as saying 3 times 1, 2, 3, 2, 5, 7, 1, 0, 8. Or if you have a matrix determinant 10, 3, minus 5, 20, 0, 6, 30, minus 1, 4, is the same as, you see this first column is a multiple, every element is a multiple of 10. So you factor out 10, and then we have 1, 2, 3, 3, 0, minus 1, minus 5, 6, and then 4. So that's how that property is applied, that if you can see that there's a row or a column that has a common factor, then the determinant is simply given by factoring out that scalar for that row, for that column, and then pull it out of the determinant and then find the determinant of the remaining matrix after factoring the scalar. So let's state the next property, and then after that property we'll do some, next session we'll do some examples. So property 5, the value of the determinant remains unchanged if to the elements of one row or column are added any constant multiple of the corresponding elements of any other row or column, respectively. This is what you mean, that if you take a scalar multiple of a row, add to another row, or you take a scalar multiple of a column, add to another column, the value of the determinant does not change. So for example, let us have the determinant A1, B1, C1, A2, B2, C2, A3, B3, C3, and then on multiplying the second column by a scalar L, and the third column by M, and adding to the first column we get, let's call it delta prime. It will be the determinant A1 plus L B1 plus M C1, then B1 C1, and then we have A2 plus L B2 plus M C2, B2, and then C2, A3 plus L B3 plus M C3. This is B3 C3. If you evaluate this determinant, you will get determinant of A1, B1, C1, A2, B2, C2, A3, B3, C3 plus L into B1, B2, B1, B1, C1, B2, B2, C2, B3, C3, B3, B3, and then C3 plus M times determinant C1, B1, C1, C2, B2, C2, C3, B3, C3. And from what you have discussed before, this determinant is 0, and this other determinant is 0. This is 0 because this first column and second column are identical, and this one is 0 because first at least we have C1, C2, C3, C1, C2, C3. So these two columns are identical. So column 1, column 2, column 3. So column 1 equals to column 3. So that's why the determinant is 0. And here, this column 1, column 2, column 3. Column 1 equals to column 2. So that's why the determinant here is 0. So therefore, this reduces to just the determinant given in the original matrix. So delta prime equals to delta. The key thing there is that when you multiply a given row or column by a scalar and then add it to another row in the determinant, then the value of the determinant doesn't change. It remains the same value of the original determinant. And then the last property for this session, number 6, if each element of a row or column of a determinant consists of the algebraic sum of n terms, the determinant can be expressed as the sum of n determinants. E.g., let delta be the determinant A1 plus P1 plus Q1 B1 C1, and then we have A2 plus P2 plus Q2 B2 C2, and A3 plus P3 plus Q3 B3 C3. So let that be the determinant. Then it can be shown that this determinant is equivalent to A1, B1, C1, A2, B2, C2, A3, B3, C3, plus P1, B1, C1, P2, B2, C2, P3, B3, C3, plus Q1, B1, C1, Q2, B2, C2, and Q3, B3, C3. So this result into this sum of three determinants. So the next session will now be doing examples on how to apply these properties we have stated in this session. Thank you.